because with the chlorination, we are doing it in the solvent, something called the chloroform, which is a non-nucleophilic solvent because it doesn't have OH groups, it doesn't have NH groups, right? It's a non-nucleophilic solvent, or you put inert solvents. So we're expecting, first thing is making a chlorine ion first. Chlorine, make a protein ion to this, either top side or bottom side. I just made it the top side. And then this chlorine ion is going to be attacked by the chloride ion that left after the first addition. And then, by the way, the chlorine ion will pull into density from these two carbon. Because of symmetry, I'm expecting both carbon will losing same amount. If it's not symmetrical, then one carbon will lose more than the others. But this one's symmetrical, so I would say 50%, 50% reaction is going to happen on either carbons. So halide, which is a chloride, attacked this one from the opposite side, right? Chlorine ion, I put it the top side. So the chloride attacked from the bottom side, makes the two chlorides added to the double bonds, but has to be trans. This is one of the eventual you create. But you don't need to show both. You can simply just show one of them. That's okay. And that's the other one. So I say there's equal possibility both will produce, but only one you can write it down. That's a simple one. But both of them will make a trans. That's the basic key. Either in enantiomers, you're never going to get a cis addition. All of them is going to be trans. So chlorination to double bonds, it's good to show that to both chlorinated, but don't use just regular line. That means the stereochemistry is not determined. At least we know that has to be trans. You're going to use a wedge and dash. You've got to show the stereochemistry because it is relevant. All right. After saying that, I really want you to look at this question carefully, and then I want you to think about these things. So let's talk about same reaction, and it's a cyclic molecule, but the concept doesn't change. The bromine, if you add it to the double bond like this, we are expecting double bonds attack the bromine, we'll get the brominium ion. The brominium ion can be top side or bottom side. 50-50 chance, but for the sake of the discussion, let's make the bromine the top side. That will pull electron density from this carbon and that carbon. But this carbon is more substituted compared to the other carbon. So which carbon will carry more positive carbon characters? The more substituted carbon. But this is the key, recognition of the carbon that will likely get affected by the nucleophile. But this time, nucleophile is a bromide, so it will make no differences, but later that will be. Anyway, the bromide, which left after the initial attack, comes back attack the more substituted carbon because of the more positive characters it forms with the bromine ion. That attack from the backside, so bromine, one bromine on this more substituted side, opposite side of the other side of bromine, so trans. So that will be the products of the added bromine to this double. Even though you make this one attack the wrong carbon, it's going to make the same thing. So you're not going to see the differences, so you thought that I can do anyway. Then there will be something that you're going to find out. The question will be, can ask you things to differently. Same thing. Now we are doing it in water. And I want you to see how things behave differently. Even in the water, still the bromine is going to attack by the pi bond first. Water is not going to attack by the pi bond because the water is not an electron deficient species. So we get the bromine ion forms first. Previously, without the water, bromide is the only nucleophile, so it attacks. Now, in water, we have a water there. Water is going to make an attack. Water is making an attack from the opposite side of the bromine ion. So anti-addition still remain the same. But it's more visible because now the water makes an attack on the more substituted side, losing one of the proton after that, you're going to see OH on the more substituted side, bromine on the less substituted side. So if you make the water attack on the wrong side, you're going to end up having a wrong product. Previously, the bromination in inner solvent, even though the bromine attack for the wrong one, you are getting the same product, so it wouldn't matter. Even though you thought wrong, it's not shown. But when you do this thing, because the different things are added into carbon, if you decide to do the wrong position, then you will end up having the wrong product. It's very easy to pick errors. So that's why we love this question. It shows your thinking process. So you can see that why the OH on the more substituted side, because it attacked from the carbocation built on the more substituted carbon. Because the more substituted carbons are better with carbocation than the less substituted carbon. So OH is here and the bromine is there. So that is basically what we just talked about, the haloform reactions, right? So this is nothing but that. So you think that, oh, there's nothing, there's no way this can be complicated. Then I'm going to show you. You can do the reactions, same bromination reactions. Bromine is here, water is there. What I did, I added extra nucleophile. I ate sodium cyanide. What is it going to make a difference? It's not going to make a difference with the bromine ion. That's going to be created. Regardless of what it is, that's the only electrophile. So pi bond is going to attack the bromine. You're going to get that no matter what is around. But this bromine ion will attack by a nucleophile. Without anything, the bromide is a nucleophile. If you're adding a water, which is solvent. Solvent means there's a plenty of solvent molecule in the solution, so water will make an attack. But now I added extra nucleophile, which is sodium cyanide. Cyanide is an even way better nucleophile, much stronger nucleophile. The water molecule may have a jet in it, but the thing is that this is going to be slow. Cyanide ion is a powerful nucleophile. Its come make an attack way better. So that makes an attack to this carbon. You got the cyanide sitting on the more substituted side, and the bromine on the less substituted side, and they're trans relationship. If you have these things swapped, it's wrong. If you get the stereochemistry wrong, that's wrong. If you get the water sitting on there, even the cyanide is used, that's wrong. Think about how many ways things can be wrong here. Only one answer is a right answer, which is this one. So that's the thing I'm talking about. It's very complicated, depending on what's the reaction conditions.